just wanted to go over a few of things on this procedure. So first, we just needed to figure out the angle of inclination. You can simply use a protractor to measure that, or you can, if you know like how far out your ramp is sticking and then how high it is, you could calculate it, but I think the protractor is probably going to be your more reliable method. So I would say that that is your priority. Okay, then here's a free body diagram for the forces. We should have, of course, gravity pulling our object down the incline. It pulls directly into the surface, and then we have a portion of that that's acting parallel to the surface. That's FGX. And then we have a portion of that that is perpendicular to the surface. That is FGY. We're also going to have a force that's acting upward. That's going to be our normal force, Fn. And then we are going to have a force that's acting up the incline. We're not really sure how big that particular one is yet. That is going to be Ff for force of friction. Okay, so we have three different forces acting on our object, but gravity, we're going to split it up into X and Y, because that way we can compare it to normal force and a force of friction. Okay, next we have the mass and the weight of the marble. Pretty much all of the marbles should be reading 0.0282 kilograms, and that is what that is in newtons. We are just multiplying by 9.8, of course, to go from mass to weight. Remember, weight is just the word for Fg. Fg stands for force due to gravity. That's weight. They are synonyms. They are the same thing. Then we figured out how much force, how much of the weight would be acting in the x direction, so acting down the incline. If this is our angle down here, this is theta down here, then FGX, that's actually the opposite side, so we would be using sine, because sine is opposite over hypotenuse, times the hypotenuse then, to get our opposite side. And then the same thing, we're going to use cosine this time, because FGY is the adjacent side, so cosine of our angle times the hypotenuse will give us the adjacent side instead. Okay, then you've got your normal force. This has to be, these two have to be the same because those forces have to be balanced. So really what's going on here is this normal force has to be balancing out this gravity force. If I moved that to right here, they should actually be the same size so that they would cancel each other out. Because we're not accelerating this way at all. We're only seeing the acceleration down the incline like that. Okay. Last question on the front is what are we going to use for a coefficient of friction? We're going to go ahead and just have everybody use mu is equal to 0.045, which is roughly where we should be getting. So instead of, there was a lot of error on the last one just because this is a lab that can have a lot of error, so we're just going to go ahead and use that standard value. All right, next, when we're calculating the force of friction, we've learned in the past we had a lot of situations where the object was at rest on the incline, and so force of friction was balancing our force due to gravity in the x direction. So like this line would be balancing this one, but that's not the case here. We don't know what the friction is, but we do know that friction can be calculated with mu and normal force. We multiply those two numbers together, we're going to get our force due to friction at this particular angle. Now let's look at what is the net force on the marble. Last class we talked about calculating net force in the y direction versus in the x direction. And we know that in the y direction, those forces are canceling out. They're balanced. There's no acceleration up from the ramp at all. But there is acceleration going in the horizontal direction parallel to the ramp. And so here we do have some net force. It's calculated by adding up the forces together, our force due to gravity in the x direction and our force due to friction. So this one here, that is going to be your answer that you got right here. And then your force due to friction is the answer that you're going to get right up here. And you're going to use those two, add those together. Of course, friction should be a negative number, so you are technically finding the difference. And then you'll have your net force. Then if you want to know your acceleration, we know that net force is equal to mass times acceleration. So we rearrange that. Net force divided by mass equals acceleration. Last thing on this page here, based on the length of the incline and the acceleration of the marble, which we're finding here, what should be the velocity of the marble if it started from rest at the top of the incline? From rest, that indicates that our initial velocity will be 0. Delta D, which is the displacement of the marble, that's going to be the length of your incline, and that's going to depend on how you set up your ramp, how steep you make it, or how pipe you actually use and keep straight. That's going to be up to you what this length is. Please make sure that you're measuring in meters, of course. And then our acceleration is the answer that you got to number 9. And then the formula that I would recommend using is the one that doesn't use time, because you don't know what that is here, and you can solve for your final velocity that way. The next thing that you needed was the centripetal acceleration. The place where the marble is most likely to fall is going to be at the very top here. If we don't have enough velocity, we're not going to make it past this point. That is the point that's really the dangerous spot. And so at that moment, your centripetal force is actually caused by the object's own weight, so gravity acting on it. And so right here, our force due to gravity is actually equal to our centripetal force. There could be maybe a little pressure or something from the ramp, but we're going to simplify things and just say that this is our centripetal force. Okay. And we're going to go ahead and say that our net force here, the only force that's really acting on the object, is going to be our centripetal force. So that is our gravity, just to simplify things here. Okay. Now we have what is the centripetal acceleration of the marble at the top of the loop. This is going to be using our formula for net force, just like we did right over here. We just need to divide by mass to get that answer. And then really you have a point where you can actually compare this well, actually, no, I'm sorry. Nope, we're not comparing yet. I got ahead of myself. Then the next thing you're doing is you're going to figure out the greatest possible radius for the loop. We know that the formula for centripetal acceleration is v squared over r. You just figured out what velocity the marble is going to have going into this loop, what that velocity is. Because that velocity going into the loop is the answer that you got to number 10. When you were finding that final velocity at the bottom of the incline, that's what this number is. Now we're using that as our answer, as our velocity in here. And I've just rearranged it to r is v squared over the centripetal acceleration. So you're taking your answer to number 10, and you're taking your answer to number 13, and plugging them into this formula. Then from there, all you're doing is actually conducting the tests. See what radius does your roller coaster need to have in order to make that work. Remember that radius is half of the diameter. So if you're measuring like that whole loop, if you're measuring like from here to here, then you're measuring the diameter. You're going to be just measuring. It's going to be hard to get it to be a perfect circle, and that's fine. You're just going to do the best that you can there. And then you're just going to test that out until you can get it to go through the loop consistently, and you know that, yes, it's actually getting enough speed to go through the loop, okay? And then that's going to be your actual radius, the half of that loop, not the whole diameter, but the half. And then you can figure out your percent error here. So comparing the radius that you calculated in number 14 as our prediction with the value that we actually observe in number 15. You're not doing a calculation here, you're making an observation here. So we're comparing those two numbers in number 16. And then you're just telling me, what do you think about where those sources of error are coming from and when we compare those. And then that is it. Thank you.